This explanation for binary operations and composite functions is way easier to understand than most textbooks.
Welcome everyone to today's explainer. Look, if you're gearing up for your algebra exams and feeling just a little overwhelmed by weird symbols and those nested, complex-looking formulas, well, you're in exactly the right place. Today, we're going to crack the algebra code by exploring what I like to call a tale of two machines. We're going to completely demystify these intimidating algebraic expressions and show you that, hey, they're really just simple sets of instructions waiting to be followed. Think of me as your enthusiastic guide today. I'm here to break down the logic step by step so you can walk into that exam room with absolute confidence. So let's just dive right in. Here is a quick look at our exam prep roadmap. 1. Cracking the algebra code. 2. One input versus two. 3. Order matters, non-commutativity. 4. Solving custom binary operations. 5. Evaluating nested composite functions. And 6. Final tips for exam success. All right, let's kick things off with Section 1, cracking the algebra code. Okay, picture this. You open your exam paper and right there in the middle of an equation is a star, or maybe a triangle, or a circle with a cross in it. It's incredibly common for students to just freeze up here. You might think, wait, did I miss an entire chapter of the textbook? But please, don't let these strange symbols scare you. They aren't some entirely new mathematical language. Actually, they're just placeholders. They represent a custom rule, like a unique mathematical recipe, invented specifically for that one single question. The symbol itself literally has no fixed meaning outside of that specific problem. Its only job is to tell you how to combine your numbers. Really, all you're doing is playing a game of substitution. You're just matching a pattern to a given rule. And once you see it that way, the anxiety completely disappears. Moving right along to Section 2, one input versus two. So let's define our first machine, the binary operation. Now, the word binary implies two, so a binary operation is just a machine that requires exactly two inputs to function. It's a custom rule that takes two distinct members of a set, which are typically represented in your exams as the variables a and b, and combines them to produce one single output. Think of it kind of like a blender. You need two different ingredients, let's say a banana and some strawberries, to blend together into one single smoothie. That, in a nutshell, is your binary operation. Now, our second machine is the composite function. And this is a bit different. A composite function is a combined nested machine. Think of it more like an assembly line. In this scenario, you put a single input into the very first machine. That machine does its work and spits out an answer. But instead of that being your final result, that output instantly drops in and becomes the starting input for the second machine in the line. It's a true two-stage process. Okay, let's dive into this side-by-side comparison, because this is absolutely crucial. A standard function machine maps just one single input, usually x, to one output. But a binary operation is fundamentally different because it strictly combines two distinct inputs, a and b, into a single output. Understanding whether you're dealing with a one-input transformation or a two-input combination is quite literally the very first step in cracking the code of your algebra exam. Which brings us to Section 3, order matters, non-commutativity. And this brilliantly illustrates the biggest trap students fall into, because you can never assume basic math rules apply here. In basic multiplication, order doesn't matter, right? 7 times 4, 4 times 7, they both give you 28. That's commutativity. But these custom operations, they're often designed to be non-commutative specifically to test your attention to detail. Take the rule, a star b equals b divided by a minus 1. Let's test 7 star 28. 7 is a, 28 is b. That gives us 28 divided by 7, which is 4. Minus 1 equals 3. Great. But what if we just casually flip the numbers and calculate 28 star 7? Now 28 is a and 7 is b. The equation becomes 7 divided by 28, which is 1/4, or 0.25. Subtract 1, and you get negative 0.75. Looking at them side by side, you can clearly see that 3 is definitely not equal to negative 0.75. Swapping the order literally changes everything. And you absolutely must remember that this non-commutative trap applies to our second machine as well. The golden rule of composite functions is that f of g of x is generally not equal to g of f of x. The order matters. Think about it like this. If you have a baking function and a frosting function, baking the cake, then frosting it gives you a delicious dessert. Frosting a pile of raw batter and then putting it in the oven, that gives you a total disaster. The order of the machines completely dictates your final output. You can't just flip them around whenever you feel like it. Let's look at Section 4, solving custom binary operations. Let's move to a real example and see how this builds a foolproof method for getting the right answer every single time. Here's our problem. Solve 7 star 28, given the rule A star B equals B over A minus 1. Step 1 is pattern matching. The number 7 is in the first position, so A equals 7. The number 28 is in the second position, so B equals 28. Step 2, we just plug those exact values right into the recipe they gave us. It becomes 28 over 7 minus 1. Finally, step 3, we calculate using standard order of operations, or BODMAS. We have to do the division first. 28 divided by 7 is 4, then we subtract the 1 to get 3. If you methodically follow these 3 steps, match, plug, calculate, you'll honestly never get tricked by a custom operation again. On to Section 5, Evaluating Nested Composite Functions. Here is an excellent classic specimen paper question. Find fg of 3, given that f of x equals 2x minus 1 over x plus 3, and g of x equals 4x minus 5. The absolute most important rule here is to work right to left. You always start with the inner function, the one sitting right next to the number. So step 1 is evaluating g of 3. We plug 3 into the g function. 4 times 3 is 12, minus 5 is exactly 7. Now for step 2. We take that answer, 7, and drop it right into the outer function, f. So we're now evaluating f of 7. Plugging 7 into the f function gives us 2 times 7 minus 1 on top, which is 13. And on the bottom, we have 7 plus 3, which is 10. 13 divided by 10 is 1.3. See? It's an elegant, nested process. Master that right-to-left flow, and these questions are going to become totally effortless for you. And finally, Section 6. Final tips for exam success. Listen, knowing the math is really only half the battle. Knowing the TROPS examiner's set is the other half. Here are the most common mistakes they are actively hoping you'll make. First, swapping input positions. As we just proved, these formulas are non-commutative, so if you casually swap A and B, you lose the mark immediately. Second, BODMAS errors. Students often get so relieved that they've substituted everything correctly that they forget the basic order of operations, like failing to divide before they subtract. And third, dropping negative signs. It happens all the time under time pressure. A simple calculation like 1 minus 4 suddenly becomes a 3 instead of a negative 3. You've got to stay vigilant. So the crucial point is how you physically approach the paper to prevent those mistakes. Here are your pro exam tips. First, literally label your inputs. Seriously, take your pen and write a tiny A and B right above the numbers on the test paper. It forces your brain to lock in the pattern matching. Second, if you see an expression with brackets, always solve the brackets first to create a new input variable before doing the next step. And lastly, for composite functions, write right to left at the top of the page so you never accidentally process the outer machine before the inner machine. Which leaves us with one final question. Are you ready to absolutely beat this substitution game? We've seen today that a binary operation is just a 2-ingredient blender, and a composite function is simply a 2-stage assembly line. These scary symbols, they're nothing more than simple rules waiting for you to follow them. And it kind of makes you think, if complex, intimidating algebraic expressions can be completely conquered just by staying organized and matching the right patterns, what other complex, intimidating systems in your life could be solved with the exact same approach? Just something to keep in mind the next time you face a difficult problem, mathematical or otherwise. Thank you so much for joining me on this explainer today. Best of luck on your exams, stay focused, and keep learning.
As always, the link for this study tool is in the description below. Let me know what you think in the comments.